Okay, I'm out here at the hotel. Well, I think everyone is hiding from the virus, but I need to give an update now on my progress in understanding reinforcement learning and the recent insights, because and specifically I want to focus on the topic of why this whole framework of training agents through reinforcement learning is a fundamental shift away from the area that I had been coming from, which is agent-based modeling. Basically designing or engineering, writing the behavioral rules of agents in a way which is hand-coded, where you're just describing the behavior, how agents will act. Where you just basically describe all the situations that they might encounter and how they will act in those situations. And there's a fundamental limitation to this, why I think this field is kind of like being replaced, or is like, at least we're kind of like coming up now with we have a better method, a better way of modeling behavior. In the case of reinforcement learning, it's very oftentimes you can get much more lifelike behavior. And one of the main things I've just realized is that has a lot to do with the high rate of decisions that the agents make. At each point in time in reinforcement learning agents, you feed in the state. In many of the problems, the state of the agent is just like what they are observing at that moment in time. And at each stage of this simulation, where you're allowing them to interact with a simulated environment, you are feeding that observation state into a neural network of some kind, and it's producing ultimately some decision, an action of which to take at that time. So I've been working with the Unity game engine, which they had discovered they made a tool back in 2017, was first released to train agents in this virtual 2D or 3D environment. And one example to illustrate this point of like the high rate of the high frequency of decisions is in one of the examples it came with or the demonstrations is the agents playing soccer. These agents that learned over many, many games of playing against each other to properly defend their goal, where they and score the ball in the opponent's goal. They learned it by just simply being rewarded when they made a goal and penalized when they were scored on. You can imagine that it's very difficult to hand code the rules in that type of a situation, because there's so many micro configurations, so many, the success in that environment is dependent on how well you can respond very quickly to a really wide array of different scenarios that happen in the game. Another example of this was in that result I referenced before about the Quake 3, the capture the flag agents, where they actually eventually learned to play better than a human team, and they actually were described as being even more cooperative than the human players. It's interesting because this represents a really fundamental departure from what agent-based modeling is and what that does, because it would be next to impossible to actually try to hand code the rules for the agents to play like that, and especially unlikely to get them to beat human players in that game. Part of why that is so different from agent-based models is that when you are hand coding behavior, it's basically like a sequence of if statements. You go and you kind of anticipate what situations the agent would find themselves in and say, if they're in this scenario, take this action, if this scenario, do this other action. So part of the difference is that it's very hard, at best, it's very difficult to actually account for all the situations that the agent could find themselves in. And then to know and then even if you can account for all of those, all those different scenarios which are relevant, to know the correct action to take such that the group or the agent can optimize their behavior to achieve their goal. So what these reinforcement learning agents are able to do is they're able to, by having this network which you give it an observation and it returns an action, you can learn effectively all these different scenarios that could come up just through the process of training, of seeing so many different games and scenarios that it eventually learns the type of things that can come up and how to respond appropriately. Ultimately, my goal would be to try to get groups of agents to work in a way which is closer to how an actual team or a complex, the complex interactions that a group has to accomplish some goal. So you kind of incentivize, somehow you have to incentivize working towards a group level objective. What types of problems would be very difficult to hand code solutions for? You need to ramp up the complexity of the environment. The complexity of the situation that an agent must respond to, because that's the case in which it's very hard for us as modelers to come up with to account for all those scenarios and to come up with a solution to how they should act in those scenarios. And so I got to thinking, what is really the definition of environmental complexity? More intuitive to think that it basically means okay, there's more stuff in the environment. Or I was thinking maybe there's just more stuff in general in the scene. But I realized that what it really means is that your ability to attain those rewards or to have success on a problem is sensitively dependent on the particularities of the configuration that the agent is in. So in the case of the soccer, it's not like there was that much stuff going on in that scene. It's a very simple situation that they're in terms of how it actually looks in the environment. But what makes that a complex environment to be trained in is the fact that their ability to gain success by getting the goal is really sensitively dependent on the micro configuration that they might find themselves in. It's kind of like a race car driver. If you're driving a race car, you're in a race, you have to be really, really present and constantly, making all these micro adjustments in order to properly, plan and move around people that you're racing against. So that's a really good problem for reinforcement learning agents, because you can get that kind of really rapid decision making and to perform those kind of micro adjustments to be successful. I guess in a way that is also a complex environment by that definition that I said, because your success is definitely dependent on these little decisions that are made. Again, it's not something which is possible in traditional agent-based modeling. You can get a high frequency of actions to be taken, but it's generally the structure of it when you're programming it is that you have a very small set of commands, the if statements corresponding to the different scenarios that the agent might encounter. And it's just not possible to really, there's just a fundamental limitation to that, is what I'm realizing. The reinforcement learning agents can begin to circumvent that by in, implicitly sort of being able to account for all those scenarios by having by having a neural network, which is, it's able to take in a pretty high dimensional, a pretty rich, data rich input and extract out what is kind of meaningful from that, and then over successive stages of processing, ultimately kind of condense it down into an ultimate decision, which is kind of pops out at the end in terms of the probabilities of the actions or the value of that particular state, or an estimation of that. I don't know if I had really known of this before I really learned about reinforcement learning more, but this idea I have, is really strong belief I have, that you can't really design complexity. I described it before as you can't engineer complex systems, you have to somehow let them evolve or let them grow or be optimized. Like, I use the example of the cell being over, how many millions of years or over the evolution of life on Earth has all these moving parts which are evolved to be there because they lead to reproduction, and it's difficult to imagine trying to design something like that, to know of all the different elements that need to be in place to really make something complex like that is really robust and really adaptive, like an organism or a cell. I think that, or I've discovered in my years of working with agent-based modeling and trying to emulate some of these natural group decisions or natural systems where you have a group that's trying to do something, it's just extremely difficult to design behavior by hand, like at the level of the agent, of the single component, that is able to that will lead to emergent group level behavior that's actually useful or that is anything close to complex. It's just extremely hard for us as humans to create that. There's a sub area about what I'm interested in, which is like multi-agent reinforcement learning. And the hope, I think, with that is that you can, by training intelligent agents, maybe you can get closer to basically evolving a group level behavior, that it can actually be more complex and more useful. So and a great example again was in that capture the flag result, where even though it's like a group of only 2 agents, you got them to perform very, very well, and it was based on training just at the individual level. So maybe we really do need intelligent agents to get intelligent groups. Like there's a whole field of swarm intelligence, which is kind of based around, in my opinion, I feel like it's based around agent-based models and trying to design intelligent groups that way by changing the individual behavior. There's all sorts of algorithms where you get these groups to solve problems, like the traveling salesman problem. They tried to solve it with ant-like agents that move along the edges, or you can have ant-based clustering algorithms where I don't know if I can find any footage of this, but basically they go off and ants will kind of cluster, brood, and cluster trash into certain areas, and you can do that with the same thing with data points in a space where you have these virtual agents go out, grab when they encounter something, and then kind of over time they just, by randomly moving around in the space, they end up aggregating a bunch of points that are of the same class or the same type. So there's these little examples of that, but I think that we can do way, way better than that now that we have the tools of reinforcement learning, because I think that developing, engineering intelligent group level behavior probably is, it kind of starts with getting really good or getting more intelligent individual behavior. What I'm working on now is I'm working on this problem where I'm trying to get these agents to learn to transport objects from one bin into another, like across a space. They're just moving in a two-dimensional space, but I'm trying to get them to learn to pass these objects to each other and find some kind of optimal solution of getting them as fast as possible across the space. And this is something which in thinking about it now, I feel like you could come up with an agent-based model to do something like this. It would be pretty involved, but you could program the behavior, like go search for your neighbor, and if they're not carrying pass it to someone who isn't carrying it, like pick the ball up from somebody who is carrying it. But the difference is with training a reinforcement learning agent group, a multi-agent reinforcement learning system, you are much more likely to be able to get not just satisfactory behavior on that task, but you may be able to get optimal behavior. So I wouldn't ever want to have my hand-coded algorithm go up against somebody who had used reinforcement learning. Like, heck no, because I know that they probably found an optimal solution, and that's part of what I'm interested in with this problem that I'm developing, is what will they do in this situation? What will be, how will they choose to solve that problem? What will an optimal solution to the problem look like? And what will happen when you scale it up in terms of more individuals in the scene? Can they adapt, using the same network to having more individuals in that scene? It's really, really exciting and crazy what the potential, the thinking about the potential for this type of technology in building intelligent multi-agent systems. Okay, I think I am piecing out. This is the Biltmore. I was trying to sit here and do some work, but then I started thinking about all this stuff. And I need to go to bed. Peace.